NASA directed some of the most capable instruments in the solar system toward 3I Atlas. Yet the first results were unexpectedly limited. Instead of the detailed structure scientists hoped to resolve, the Mars Reconnaissance Orbiter's HiRISE camera returned an image that appeared as a diffuse, featureless glow. This outcome surprised researchers because HiRISE routinely captures sharply defined surface features on Mars, including rocks and sediment patterns only tens of centimeters across. Under normal circumstances, the instrument should have been able to extract at least basic structural information from the coma of an active object tens of millions of kilometers away. At the same time, amateur astronomers on Earth began sharing their own observations. Using consumer-grade telescopes and readily available image stacking software, many reported capturing faint geometric jets extending outward from the object, as well as ring-like features encircling what appeared to be its central region. These independently produced images showed shapes and symmetries that did not appear in NASA's official data. Although such observations require careful verification, the consistency across multiple amateur reports raised questions that could not be ignored. The contrast between high-end and low-end observations quickly became the core of what some researchers informally termed the visibility paradox. At its heart lies a simple mismatch. Instruments engineered for precision recorded very little, while much simpler systems seem to reveal structure. Such a discrepancy can occur for several reasons, but the scale of the difference suggested a deeper physical mechanism affecting what each type of sensor could detect. One of the leading explanations proposes that 3I Atlas may be surrounded by a dense, dynamic plasma environment capable of scattering and diffusing incoming light. Plasma, composed of ionized gas and charged particles, interacts strongly with electromagnetic radiation. Under certain conditions, it can blur or dampen signals captured by high-resolution instruments that rely on short exposures and specific wavelengths. Ground-based amateur equipment, which often integrates exposures over longer periods and works across different spectral ranges, might then capture structural hints that spacecraft imaging smears into a uniform haze. This idea becomes more relevant given the timing of expected solar activity. A significant solar storm was forecast to reach the inner solar system within days of the first NASA images. Solar storms can disturb plasma envelopes around comets, compressing or dispersing them depending on the orientation and strength of the incoming magnetic field. If 3I Atlas does possess such a plasma shell, the storm could temporarily reduce its density or disrupt its stability, potentially revealing features hidden during earlier observations. Conversely, it could increase the opacity and make the object even more challenging to image. In either case, the event represented a unique opportunity to test the hypothesis. The broader context makes 3I Atlas particularly important. Before 2017, no confirmed interstellar objects had ever been observed entering our solar system. The detection of 1I Oumuamua marked the beginning of a new field of study. That object displayed unexpected behavior, including a small but measurable acceleration inconsistent with standard gravitational models, and lacked the typical coma expected from icy bodies. 2 years later, 2I Borisov entered the system, presenting as a more conventional comet but with chemical signatures that diverged from the comets typically seen in the solar system. Now, 3I Atlas arrives as the third known interstellar visitor, and early data suggest it is the most complex and unusual of the three. Its motion shows signs of non-gravitational acceleration. Its composition, particularly its carbon dioxide to water ratio, is outside the range observed in solar system comets. Its polarization signatures indicate particle properties not well represented in cometary databases. And now, its visibility profile adds another anomaly to the list. The initial observations began on November 19, 2025, when NASA released the first image set from the Mars Reconnaissance Orbiter. The view showed 3I Atlas as a faint, unresolved patch of light. At roughly 30 million kilometers, the object spanned only a small number of pixels in the image, but the lack of distinguishable coma structure was still unexpected. Scientists gathered data from complementary instruments as well. Ultraviolet observations from MAVEN revealed a hydrogen envelope typical of water-driven sublimation, and Perseverance captured a faint streak across the Martian sky as the object passed in its field of view. These data points independently confirmed that the object was active and shedding volatile gases, aligning with comet-like behavior. Yet they did not clarify why high-resolution imaging produced so little detail. From Earth, the discussion quickly shifted toward reconciling the two extremes. Ground-based images showing hints of structured activity and orbital imagery showing almost none. The situation highlighted how strongly an object's surrounding environment can influence observational results across different platforms. Amateur observations continued accumulating during this period. Many observers used filters that emphasize emission from specific molecules or dust distributions. Others employed long exposure times that increase sensitivity to faint extended features. As these images circulated online, several recurring patterns appeared: jets emerging at consistent angles, asymmetries in the coma, and faint circular or spiral arrangements around the nucleus region. While no single image can serve as definitive evidence, the number and diversity of sources reporting similar features made the reports worthy of scientific consideration. The question emerged: could the difference be entirely due to observational methodology, or was something unique occurring around 3I Atlas itself? Differences in distance, exposure duration, wavelength sensitivity, and processing techniques can all lead to variation, but these typically explain a range of detail, not a total inversion where the most advanced instruments see the least. This led some researchers to examine the possibility that the medium around the object, not the object's core, was responsible for the mismatch. If a dense, unevenly distributed plasma region surrounds the nucleus and inner coma, it could cause scattering that affects short exposure. High-resolution imaging, far more than long-exposure amateur observations. Such scattering would act like a dynamic fog, smoothing out fine structure. Under this interpretation, both sets of observational data could be correct. The structure is genuinely present, but professional spacecraft are simply observing it under conditions where the plasma interference is at its strongest. As the solar storm approached, attention turned toward time-sensitive monitoring. Plasma environments around comets respond rapidly to changes in solar wind pressure and magnetic field orientation. A sufficiently strong disturbance can compress, distort, or remove sections of plasma, altering the visibility of the underlying material. For researchers seeking clarity on 3I Atlas, the storm offered a natural experiment. If the object's appearance changed significantly, it would provide direct insight into how much of the observed blur originated from environmental effects rather than instrumentation limits. The situation embodies a broader lesson of observational astronomy. What we see depends as much on the conditions between observer and target as on the target itself. In the case of 3I Atlas, the interplay among solar activity, plasma physics, and instrument capabilities created a scenario where interpretation required caution and multi-wavelength, multi-platform comparison. Whether the visibility paradox ultimately reflects a unique property of the object or simply the limits of our tools, the early stages of observation made clear that 3I Atlas would challenge assumptions across disciplines. The next stage in understanding 3I Atlas requires examining the early data in detail, beginning with NASA's November 19, 2025 imagery release and the public reaction that followed. The agency described the results cautiously. According to the press statement, the high-rise camera aboard the Mars Reconnaissance Orbiter had successfully captured observations from an unprecedented vantage point, viewing an interstellar object from Mars orbit. The language emphasized engineering achievement rather than scientific clarity because the image itself revealed very little structure. At a resolution of roughly 30 kilometers per pixel, the object appeared as a diffuse patch of reflected sunlight, only about 10 pixels across. No nucleus was resolved. No jets or morphological details emerged. The coma blended into the background without identifiable features. From a technical standpoint, this result is consistent with expectations at such distance and scale, but it nonetheless contrasted sharply with public hopes for a clearer view. NASA supplemented the release with supporting data from other instruments. UV observations from the MAVEN spacecraft identified a hydrogen envelope around the object, indicating active water sublimation. This is standard for comets approaching the Sun and is consistent with natural outgassing processes. On the Martian surface, the Perseverance rover detected a faint streak in the sky as 3I Atlas passed through its observational window, providing yet another indirect confirmation of the object's trajectory and activity. These findings helped establish a coherent picture of a small active body producing gas and dust. However, they did not resolve the mismatch between professional and amateur observations. Within hours, discussions erupted across social platforms, scientific forums, and astronomy communities. Responses split into several distinct groups. One segment focused on the technical achievement itself. Observers noted that coordinating multiple spacecraft around Mars To track a fast-moving interstellar object was no small task. They highlighted the complexity of pointing and stabilizing orbital instruments designed primarily for surface imaging and atmospheric studies. For these individuals, the data represented meaningful progress in interstellar object science. Another group expressed dissatisfaction. Many questioned why an instrument capable of measuring surface details on Mars with exceptional clarity produced such limited results when pointed at 3I Atlas. Some argued that NASA's cautious framing signaled underlying uncertainty or disappointment. Others speculated without evidence about withheld data or incomplete releases. These reactions were amplified by the circulating amateur observations showing more structure than NASA's imagery seemed to detect. Amateur astronomers continued to present images highlighting potential jets, rings, and asymmetries. Some captured apparent rotational patterns or changes in brightness over time, suggesting dynamic processes within the coma. While variations in amateur data quality make interpretation difficult, the repeated appearance of similar features across independent observers gave the reports moderate credibility. The contrast sharpened the central question: why would ground-based images with lower baseline resolution show more detail than orbital images from Mars? Professional astronomers responded by clarifying the limitations of spacecraft imaging. HiRISE is engineered for high-resolution surface mapping at distances of a few hundred kilometers, not detailed capture of small, faint targets tens of millions of kilometers away. Its brief exposure times, narrow wavelength range, and motion-compensated imaging design restrict its ability to collect faint extended features around an object like 3I Atlas. In practical terms, using HiRISE for this purpose is similar to aiming a microscope at a distant moving aircraft. The instrument is simply outside its optimal use case. Amateur observers, by contrast, often rely on long integrations, stacking hundreds of frames to amplify faint signals. They can also adjust filters, exposure times, and processing techniques to emphasize subtle variations. While atmospheric distortion reduces baseline resolution, long exposure averaging can reveal large-scale structures that remain invisible in short snapshots. This methodological difference alone can explain part of the discrepancy. However, the difference in methodology may not be the sole factor. The visibility paradox gains weight when considering reports that the structural features observed by amateurs persisted across multiple nights and multiple observers using diverse equipment. This consistency suggests that at least some coma structures might genuinely exist, rather than being artifacts of processing or atmospheric conditions. If those structures are real, the question becomes why HiRISE and potentially other high-resolution systems failed to detect them. One proposed answer again points to environmental effects. A plasma-rich coma could scatter visible light in ways that disproportionately degrade short-exposure imaging. High-resolution systems depend on sharp photon paths, while long-exposure systems can accumulate enough integrated signal to overcome certain types of scattering. Under this interpretation, both observational modes reveal different aspects of the same object due to the interaction between light and the surrounding plasma. The public debate also brought forward more speculative ideas, including claims of data suppression or selective reporting. While such theories gained traction online, there is no evidence that data was withheld. The simpler explanation aligns with observational constraints, instrumental limitations, and the physics of plasma scattering. NASA released the images available at the time, and additional data will follow standard processing and review protocols. Nonetheless, the skepticism highlights how the expectations of the public have evolved. Modern astronomy has accustomed audiences to spectacular imagery. Detailed views of galaxies billions of light-years away, direct images of exoplanets, and precise visualizations of black hole shadows. When confronted with a near-featureless view of an object only tens of millions of kilometers away, people naturally question the outcome. The gap between public expectation and scientific reality becomes a fertile ground for speculation. A key insight is that visibility is not solely determined by distance or instrument power. The medium between observer and object, especially when plasma is involved, can distort or obscure structure in complex ways. A densely ionized coma with active interactions between dust, gas, and charged particles can create an environment in which large-scale patterns are visible only under specific observational circumstances. This perspective reframes the amateur-professional discrepancy. Amateur observations showing jets and ring-like features may be capturing moments when the plasma density is lower, turbulence has decreased, or the observation angle minimizes interference. Spacecraft instruments, observing from different geometries and with shorter exposure times, may encounter the object during less favorable conditions. In this scenario, neither dataset is incorrect. Both are partial views shaped by environmental variability. As interest grew, attention shifted toward the upcoming solar storm expected around November 22nd. Solar storms alter the density, pressure, and magnetic structure of the solar wind. For an object like 3I Atlas, which appears to be highly sensitive to solar wind interactions, the storm could dramatically reshape its surrounding environment. If plasma scattering is responsible for the visibility paradox, the storm could either clarify or complicate the view. A drop in plasma density might expose jets or the nucleus, while a compression event might create new transient structures. Either outcome provides scientific value. A sudden increase in visibility would support models linking scattering to plasma density. A further degradation of visibility would indicate strong environmental sensitivity. No change at all would argue against plasma being the dominant factor. Thus, the solar storm serves as an opportunity to test hypotheses that otherwise would remain speculative. In summary, the early observational phase of 3I Atlas revealed more about the challenges of perception than about the object itself. It demonstrated how different observational methods produce complementary yet sometimes contradictory insights. It showed how plasma environments can complicate imaging, and it highlighted how public expectations shape the interpretation of scientific data. As new observations accumulate, The goal remains to integrate these disparate perspectives into a coherent scientific understanding. To understand why 3I Atlas appears so differently across various instruments, we need to explore the idea that has emerged as one of the most discussed possibilities: the plasma shield hypothesis. Although the term may sound speculative, the concept itself is grounded in well-established plasma physics. The hypothesis proposes that 3I Atlas is enveloped by a region of dense, energized plasma capable of altering or degrading incoming light in wavelength-dependent ways. Plasma, in an astrophysical context, is ionized gas composed of free electrons and ions. It represents the most common state of matter in the universe. Plasma responds strongly to magnetic fields and electromagnetic radiation, and its interaction with light can be complex. For example, plasma can scatter photons, absorb energy, or change the path of light passing through it. These effects depend on electron density, temperature, magnetic field strength, and the wavelength being observed. In the case of 3I Atlas, a plasma-rich environment could arise naturally through outgassing the release of volatiles from the surface as the object approaches the Sun. Ultraviolet radiation and solar wind particles ionize the expanding gas, producing charged particles that form the object's ion tail. In most comets, this ion tail is clearly visible and points directly away from the Sun due to solar wind pressure. However, if the composition of 3I Atlas differs significantly from typical solar system comets, the resulting plasma distribution may be much denser or more irregular than expected. Its unusually high carbon dioxide content, for instance, could alter the ionization balance. Under certain conditions, the plasma may not be swept away efficiently by the solar wind, but instead accumulate around the nucleus, forming a thickened region that behaves like a scattering layer. This kind of plasma environment could blur high-resolution imagery without eliminating the overall brightness of the coma. Professional spacecraft instruments, which rely on short exposures and operate in specific wavelengths, would be the most impacted. Amateur telescopes using longer exposures and different spectral bands might still detect variations in brightness that correspond to real structural features beneath the plasma layer. The concept also helps explain the reported variability of 3I Atlas. Plasma is inherently dynamic. Its density and structure can change rapidly in response to variations in the solar wind. Observers across different time zones and continents have noted changes in the coma's shape, brightness, and symmetry over short time periods. These variations may not reflect changes in the nucleus itself, but instead shifts in the surrounding plasma environment as it interacts with solar wind fluctuations. Although the plasma shield hypothesis remains unconfirmed, it is empirically testable. Plasma emits light at characteristic wavelengths. If the environment around 3I Atlas is as dense as the hypothesis suggests, observers should detect identifiable spectral lines associated with ionized species, such as CO+, CO2+, or H2O+. Similarly, radio observations may reveal dispersion effects or other signatures consistent with dense plasma. So far, however, the evidence is limited. Existing observations detect only the expected ionized species at normal intensities, with no unambiguous indicators of extreme plasma density. There are challenges to the hypothesis. One is energy. Maintaining a dense plasma envelope requires continuous ionization, which demands a significant supply of energetic particles. The Sun provides a substantial portion of this energy, but whether it is sufficient to sustain the level of plasma implied by the visibility paradox remains an open question. Another challenge is stability. Plasma tends to be turbulent. Maintaining a cohesive shell would require a balance of forces not typically observed in natural comets. Despite these limitations, the hypothesis remains compelling because it accounts for several observational anomalies simultaneously. It also aligns with the practical differences between amateur and professional observations. The latter depend heavily on high-contrast imaging and precise photon capture, both of which are sensitive to scattering. The former integrate faint signals over longer periods, effectively smoothing out noise introduced by plasma turbulence. The plasma shield hypothesis also introduces a more general point. Our ability to observe an object depends not just on its inherent properties, but on the environment surrounding it. When an object travels through a medium of varying density and composition, the medium becomes a limiting factor. This perspective underscores the importance of multi-wavelength observations, especially when dealing with interstellar objects whose behavior may differ significantly from familiar solar system bodies. As 3I Atlas moves through the inner solar system, its plasma environment may evolve in ways that reveal or obscure features unpredictably. This makes the upcoming solar storm particularly relevant. A significant disturbance in the solar wind could compress or disperse the plasma surrounding the object. If the plasma shield exists, the storm may temporarily disrupt it, revealing the nucleus or inner structures otherwise hidden from view. Conversely, the storm could increase plasma density and further obscure the object. If clear structural features appear during the storm, such as jets, fans, or asymmetric outflows, it would strengthen the case for plasma-mediated visibility effects. If the object remains featureless across all wavelengths, the hypothesis would face substantial challenges. Either way, the solar storm offers a natural experiment with the potential to clarify a central mystery. Expanding on the broader context, the plasma shield hypothesis raises an important question. How do we interpret ambiguous observational data when an object falls near the limits of our current technology? The case of 3I Atlas highlights the need for caution. Without understanding the environmental conditions, researchers risk misattributing observational limitations to the object's inherent properties. This caution also extends to more speculative interpretations, including claims of artificial origin. While plasma-based cloaking is theoretically possible, there is no evidence indicating intentional mechanisms at work. All observed phenomena can be explained through natural processes, including outgassing, ionization, and solar wind interactions. Nonetheless, the unusual interplay between environmental conditions and observational technology encourages careful analysis. Ultimately, the plasma shield hypothesis does not claim that 3I Atlas is fundamentally different in nature from typical comets. Instead, it suggests that environmental factors unique to this object, possibly tied to its interstellar origin, affect how it appears to different observers. The hypothesis serves as a reminder that even familiar processes can produce unfamiliar outcomes under the right conditions. Examining these environmental effects also contributes to a broader understanding of interstellar objects. The behavior of 3I Atlas illustrates that objects formed around other stars may interact with the solar environment in ways that challenge existing models. This reinforces the importance of adaptable observational strategies that account for diverse physical conditions. As research continues, the key question is whether the plasma shield hypothesis can be connected to measurable signatures. Multi-wavelength data, particularly from radio, infrared, and ultraviolet instruments, will be essential. Detailed spectroscopic analysis will help determine the density and composition of the plasma. Time-resolved imaging will reveal how rapidly the environment evolves. These approaches will allow researchers to evaluate whether plasma scattering is the primary driver of the visibility paradox. Until then, the hypothesis remains an informed interpretation rather than a confirmed mechanism. It provides a coherent framework that unites several puzzling observations but requires further evidence. The upcoming solar storm, ongoing amateur monitoring, and scheduled observations from professional observatories will supply the data necessary to evaluate the hypothesis rigorously. As with many scientific debates, progress depends on continuous observation, careful analysis, and the willingness to revise assumptions based on new information. Understanding 3I Atlas requires not only examining its internal processes, but also recognizing how strongly it is influenced by its surrounding environment, particularly by the solar wind and upcoming solar activity. As the object moves through the inner solar system, the Sun is approaching a period of heightened activity, with a significant solar storm predicted to arrive around November 22nd, 2025. This timing is critical because a solar storm can substantially alter the plasma conditions around a comet-like object. Solar storms begin with coronal mass ejections, CMEs, events in which the Sun expels large quantities of magnetized plasma into space. These structures travel outward at speeds that can exceed 1,000 km/s. When a CME reaches the inner solar system, it interacts with everything in its path: planetary magnetospheres, spacecraft, and cometary environments. Because CMEs carry embedded magnetic fields, their arrival can alter the plasma density, temperature, and pressure around smaller bodies. For most comets, these interactions produce noticeable changes. The ion tail may shift direction or develop new structures. In some cases, CMEs cause disconnection events, moments when the entire ion tail detaches and drifts away before reforming. CMEs can also increase the overall brightness of a comet by accelerating ionization processes within the coma, making it more visible in ultraviolet and optical wavelengths. If 3I Atlas indeed possesses an unusually dense or structured plasma environment, the predicted solar storm represents a natural test. Depending on the characteristics of the CME, its speed, density, magnetic field orientation, and arrival angle. It could compress the plasma around the object, disperse it, or trigger rapid changes in outgassing behavior. Each outcome carries distinct observational signatures. Scenario 1. The storm strips or thins the plasma environment. If the CME's magnetic field interacts in a way that pushes plasma outward or disrupts any coherent structure, telescopes may finally capture the nucleus or internal jets previously obscured. A sudden increase in visible detail would support the hypothesis that the visibility paradox is driven by plasma scattering. Scenario 2. The storm compresses the plasma, increasing opacity. In this case, the object could become even more difficult to resolve. Increased scattering might broaden the coma, reduce contrast, and suppress faint structural features. Even if outgassing increases due to heating or other induced effects, the visual result may be a more uniform and obscured object. Scenario 3. The storm triggers transient features unrelated to the nucleus. A CME can generate temporary structures, loops, filaments, or rotating patterns within the plasma surrounding a comet. These shapes may resemble jets or shells but lack direct connection to the nucleus itself. Distinguishing these artifacts from genuine structural features requires careful monitoring and multi-wavelength imaging. If such features appear during or immediately after the storm, observers must consider whether they result from external forcing rather than intrinsic processes. Across all scenarios, coordinated monitoring will be essential. Professional observatories will attempt to allocate observation time, while amateur networks may provide continuous coverage when large telescopes cannot. As the storm approaches, operators of solar observation missions such as STEREO, SOHO, and the Solar Dynamics Observatory will track the CME's trajectory and properties. Their data will help model how the storm interacts with 3I Atlas and predict when and where changes might occur. A solar storm also interacts with the comet's non-gravitational acceleration. Outgassing-driven forces already influence the object's trajectory, producing measurable deviations from a purely gravitational path. If a CME significantly alters outgassing rates, either by heating the surface, changing the plasma distribution, or modifying the solar wind pressure, these forces could shift abruptly. Researchers may observe temporary acceleration changes, modifications in the spin state, or variations in the apparent direction of the tail. These changes would provide additional clues about the physical processes shaping the object's behavior. The solar storm also serves as a reminder of the environment through which 3I Atlas is traveling. Space is often perceived as empty, but the region between planets is filled with charged particles streaming from the Sun and shaped by the heliospheric magnetic field. This medium plays an active role in how small bodies evolve and how we observe them. The response of 3I Atlas to the storm will help clarify whether the visibility paradox reflects intrinsic properties of the object or the dynamic conditions around it. The predicted timing adds urgency. The storm is expected within approximately 72 hours of the first NASA image release, a narrow window that gives observers little time to adjust. Still, This period creates an opportunity for real-time comparison, observing 3I Atlas before, during, and after the disturbance. If features become visible only after the storm, the change could offer strong evidence supporting plasma-related obscuration effects. If, however, the comet remains unchanged across the entire event, the hypothesis faces a significant challenge. A stable appearance would suggest that plasma density is not the dominant factor shaping visibility, or that the structure, if present, is inherently concealed by dust or other material not easily affected by solar wind pressure. Regardless of the outcome, the event provides valuable data. Even a lack of variation offers constraints that help refine models of the coma and its interaction with solar wind. Space weather events serve as natural experiments that highlight the complex relationship between solar activity and small bodies. The storm also underscores the importance of observational coordination. Solar storms are global events in the heliosphere, affecting all observers and instruments. Coordinated campaigns involving professional observatories, space-based telescopes, and amateur networks enable comprehensive monitoring across wavelengths and time zones. For 3I Atlas, such collaboration increases the probability of capturing transient changes and improves the quality of data available for modeling. Looking ahead, the role of solar storms in shaping observations of interstellar objects will continue to grow in importance. As more interstellar visitors are detected in coming years, researchers will confront new cases in which solar activity influences appearance, composition signatures, or trajectory calculations. A better understanding of how solar wind affects these objects will help distinguish intrinsic properties from environmental interactions. The upcoming storm is also a reminder of the broader vulnerability of spacecraft and infrastructure. Solar storms can affect Mars orbiters, Earth satellites, and power systems on our planet. Missions observing 3I Atlas must adapt to increased radiation levels, changes in atmospheric density, and heightened risk of instrument noise or data corruption. These operational challenges highlight the interconnected nature of heliophysics and planetary science. For 3I Atlas, the storm represents a key moment. Whether or not it reveals new information about the object, it will shape the scientific narrative. If visibility improves, it will reinforce the idea that the object's environment plays a central role in how we observe it. If visibility worsens, researchers will need to reconsider the weight of environmental factors. And if nothing changes, new hypotheses will emerge to explain the persistent lack of detail. Ultimately, the solar storm demonstrates that even with advanced instruments and coordinated global efforts, the space environment itself remains a variable that can obscure, reveal, or distort the phenomena we seek to study. Understanding these interactions is essential for interpreting the behavior of interstellar objects and for expanding our observational capabilities as new, faster, and more chemically diverse visitors enter our detection range. Up to this point, the study of 3I Atlas has focused on its visibility issues, the contrasting observations from professional and amateur sources, and the potential role of plasma in modulating what different instruments can detect. These topics form the foundation for understanding why the object appears as it does. Before expanding the investigation into more technical areas, it is useful to summarize the terrain covered so far and outline the direction of the next stages of analysis. The central question driving early discussion is the visibility paradox, the mismatch between what sophisticated spacecraft cameras observe and what amateur telescopes appear to show. This paradox suggests that either our expectations of instrumentation must be recalibrated, or that the environment around the object influences observations in ways not previously accounted for. NASA's November 19th imagery confirmed the object's position and activity, but offered little structural detail. Public reaction diverged between appreciation of the engineering achievement and disappointment at the lack of clarity. Amateur astronomers, meanwhile, continued to present images with apparent structural hints, jets, asymmetric features, and ring-like patterns. While these observations must be weighed carefully due to variability in conditions and processing, many displayed consistent elements across observers and regions. The plasma shield hypothesis offers one possible explanation for the differences by proposing that the environment around the object affects high-resolution imaging more than long-exposure ground-based observations. The upcoming solar storm event adds time sensitivity to the investigation. A CME can modify a comet's plasma surroundings by compressing or dispersing charged particles, potentially revealing or concealing structures. This event provides an opportunity to evaluate multiple hypotheses at once. Whether plasma scattering accounts for blurred professional images, whether amateur features persist under altered conditions, and whether the object's activity profile changes significantly. With these foundational topics introduced, the next stage of analysis shifts into the technical anomalies associated with 3I atlas properties that extend beyond visibility. These anomalies include the object's non-gravitational acceleration, polarization signatures, chemical composition, and behavior across wavelengths. Each of these factors deviates sometimes subtly, sometimes significantly, from what is typically observed in solar system comets. A structured investigation begins by examining non-gravitational forces, which represent measurable deviations from a purely gravitational trajectory. Most active comets experience such deviations due to momentum transferred by escaping gas and dust. In the case of 3I Atlas, the observed acceleration does not align cleanly with standard outgassing models. Either the nucleus is venting material at unusual rates, or the distribution of jets is more concentrated or directional than expected. Clarifying this behavior requires detailed modeling of mass loss rates, exhaust velocities, and jet geometry. The next major topic involves polarimetry, the study of how light becomes polarized when it reflects off particles in the coma. Polarimetric measurements of 3I Atlas show values outside the usual range observed in comets and asteroids. These findings indicate differences in particle size, shape, or composition that may relate to the object's interstellar origin. Following that, the investigation moves into composition, where perhaps the most striking anomaly emerges. the unusually high carbon dioxide to water ratio observed in early spectroscopy. Typical solar system comets contain far more water ice relative to carbon dioxide. The composition of 3I Atlas places it far outside standard distributions, raising questions about its formation environment. This anomaly is consistent with the possibility that the object originated far from its parent star, in a region analogous to the outermost parts of the Kuiper Belt or beyond. Act 2 of the investigation will therefore focus on these deeper technical deviations. Each anomaly can be explained individually by rare but plausible natural conditions limited data, a unique initial composition, or the effects of long-term cosmic ray processing. However, the combination of multiple unusual features challenges simple explanations. Together, they create a profile that differs significantly from typical comets observed within the solar system. At this stage, the analysis questions whether these anomalies reflect natural variation among interstellar objects or whether 3I Atlas occupies an edge case in parameter space. For example, cosmic ray processing in interstellar space could alter the surface chemistry of an object over millions of years, generating the organic-rich crust and volatile depletion patterns that some observations imply. If this process can increase CO2 abundance relative to water, this could explain the unusual ratios observed. Another topic that enters the discussion is the speculative idea of artificial origin. This concept has been raised primarily because interstellar objects sometimes display properties that are difficult to match with existing models, as was the case with 1I Oumuamua. Although no evidence supports an artificial explanation for 3I Atlas, the topic surfaces naturally when dealing with outlier behavior. A thorough, balanced approach requires acknowledging such possibilities without assigning them undue weight. As part of the broader narrative structure, Act 2 will also examine the viability of the plasma shield hypothesis in more technical detail. This will involve a deeper look at how plasma might form stable or semi-stable structures around an object, how magnetic fields could influence its distribution, and how various wavelengths respond to scattering. Additional observational challenges must be addressed, such as why spectroscopic emissions do not show extreme ionization levels predicted by the densest plasma models. Finally, the investigation will consider the broader context of interstellar object science. With only 3 confirmed interstellar visitors detected so far, statistical expectations remain uncertain. As next-generation survey telescopes come online, more objects will be discovered, offering a larger sample to evaluate whether 3I Atlas represents a rare type or a category of objects that has simply been undersampled. Understanding these trends will shape the interpretation of current anomalies. In summary, the roadmap ahead includes several interconnected lines of inquiry, analysing non-gravitational acceleration and mass loss rates, interpreting unusual polarization characteristics, examining composition anomalies, evaluating plasma interactions, and assessing environmental effects such as solar storms. Each of these topics will contribute to building a comprehensive picture of the object's physical nature and behavior. The transition into these deeper discussions marks a shift from observational questions, what we see and why, to physical interpretations of what 3I Atlas is made of, how it formed, and how it interacts with the solar environment. As the investigation continues, combining multi-wavelength observations, modeling, and cross-disciplinary analysis will be essential. The ultimate aim is to reconcile the unusual features of the object with coherent physical explanations anchored in known processes. Whether the anomalies reflect a rare but natural combination of conditions, or whether they hint at previously unrecognized categories of interstellar material, the next stages will bring more clarity. The analysis will then move into specific technical findings, beginning with acceleration, mass estimates, and the mathematical basis for these deviations. A deeper understanding of 3I Atlas begins with the forces influencing its motion. While its trajectory is broadly consistent with an interstellar object passing through the solar system, precise tracking has revealed measurable deviations from a purely gravitational path. These deviations fall under the category of non-gravitational acceleration effects produced when an active comet expels gas and dust. As material escapes the nucleus, it carries momentum, generating a recoil force that alters the object's velocity. This mechanism is well established and is routinely used to model the motion of many comets. For 3I Atlas, however, the magnitude of non-gravitational acceleration is slightly higher than expected based on the observed activity. This discrepancy does not represent a dramatic contradiction, but it does fall outside comfortable margins. To understand the issue, it is useful to examine how mass loss translates into measurable forces. The basic principle is straightforward. The force exerted on the nucleus equals the mass flow rate multiplied by the exhaust velocity of the escaping material. By measuring the object's trajectory and comparing it to predictions based solely on gravitational influences, researchers can determine the additional acceleration required to match observations. From that acceleration, they can calculate how much mass the object must be losing and in which direction. Initial analyses estimate the dust production rate of 3I Atlas at approximately 180 kilograms per second when the object is at a distance of 2 astronomical units from the Sun. This value is high but not unprecedented. For comparison, Comet 67P Churyumov-Gerasimenko displayed similar production rates when observed by ESA's Rosetta mission. The challenge lies in connecting these numbers to the estimated size of the nucleus. The nucleus of 3I Atlas has not been directly imaged. Its size is inferred from brightness and assumed reflectivity, albedo. If the albedo is low, the nucleus must be larger to account for the observed brightness. If the albedo is higher, the nucleus could be significantly smaller. Depending on the assumed values, size estimates range from roughly 1 to 4 kilometers. This uncertainty means that the mass loss rate could be either entirely reasonable or somewhat high for an object of its size. A smaller nucleus losing 180 kilograms per second would experience stronger recoil forces relative to its mass, leading to greater non-gravitational acceleration than typically seen. A larger nucleus would require proportionally more mass loss to generate the same acceleration. This sensitivity to size assumptions makes the calculations delicate, and until the nucleus is directly measured, the uncertainties remain. Another factor to consider is the distribution of jets. A uniformly active surface produces only moderate acceleration because material escapes evenly in all directions. Many comets, however, emit gas and dust through localized vents or jets. These concentrated outflows can produce significant directional forces even with modest mass loss rates. If 3I Atlas has strong jets oriented toward or away from the Sun, the observed trajectory could be explained without invoking unusual physics. The difficulty is that clear jets have not yet been confirmed in professional imagery. NASA's HiRISE data shows no resolved structures. Only amateur images suggest jet-like features, and their reliability remains uncertain. If jets do exist, but are obscured by a dense plasma environment, as proposed in earlier sections, this could reconcile the observations. Under such conditions, jets might produce acceleration consistent with the data while remaining hidden in high-resolution imaging. Some researchers have raised more speculative possibilities involving magnetic interactions. If 3I Atlas possesses an intrinsic magnetic field, or if its plasma environment interacts strongly with the solar wind, additional forces could arise independent of mass loss. Magnetic tension, plasma drag, and induced currents can all generate small accelerations under the right conditions. However, these effects are typically relevant only at very small scales or in extremely dense plasma regimes. No known natural comet exhibits significant magnetic forces comparable to recoil from outgassing. A more exotic line of speculation proposes artificial propulsion mechanisms, but there is no evidence supporting such an interpretation. Natural processes provide ample explanation for the observed acceleration once uncertainties in nucleus size, jet distribution, and plasma effects are considered. A related issue involves the momentum budget over time. To maintain the observed deviation from a gravitational path, the object must lose a measurable amount of mass across its journey through the inner solar system. If the total mass lost becomes too large relative to the estimated mass of the nucleus, the model becomes inconsistent. Early calculations suggest that 3I Atlas remains within reasonable bounds. Even with higher than average outgassing rates, the total mass lost across its active period likely represents only a small fraction of its total mass, assuming the nucleus is at least a few kilometers across. Another layer of complexity arises from how activity scales with solar distance. Water-driven comets typically follow a specific pattern. Activity increases rapidly as they approach the Sun. The rate often follows a power law related to the amount of solar radiation received. In the case of carbon dioxide or carbon monoxide-driven comets, the activity profile can be steeper because these ices sublimate at lower temperatures and can dominate the outgassing earlier in the approach. 3I Atlas appears to follow a steep activation curve, consistent with CO2 or CO-dominated sublimation. This behavior supports earlier spectroscopic findings indicating unusually high carbon dioxide abundance. Stronger CO2 sublimation also supports higher mass loss rates at larger distances from the Sun, aligning with the observed acceleration. Together, these factors highlight a central challenge. The acceleration data does not point to a single definitive conclusion. Instead, it narrows the range of possibilities. If the nucleus is small, the object must be highly active, emitting dust and gas at a rate near the upper edge of natural models. If the nucleus is larger, the observed acceleration becomes easier to explain. Determining which scenario is correct requires additional constraints from direct imaging or more refined brightness modeling. Importantly, none of the acceleration anomalies necessarily indicate anything unnatural. The values fall within plausible limits for an interstellar comet, particularly one with unusual composition and potentially dense plasma interactions. Interstellar objects may experience extensive cosmic ray processing, leading to volatile distributions different from those of solar system comets. These differences can drive higher than expected outgassing rates under certain conditions. The mathematical analysis of acceleration therefore becomes one part of a larger pattern. Each anomaly acceleration, composition, polarization, visibility can be explained individually. The challenge is integrating them into a coherent model that accounts for all available data. If the plasma shield hypothesis is correct, and if CO2-driven sublimation dominates the object's activity, then the observed acceleration fits comfortably within natural expectations. The next stages of investigation will examine additional physical signatures that further illuminate the object's composition and surface properties. Polarization data, spectral analysis, and coma morphology will provide more clues about particle size distributions, chemical makeup, and environmental interactions. A clearer understanding of 3I Atlas requires examining how the object reflects and polarizes sunlight. Polarimetry, the study of how light becomes polarized after interacting with particles, offers insight into the size, composition, and structure of dust in the coma. In the case of 3I Atlas, polarimetric measurements reveal behavior significantly different from that of known comets and asteroids, suggesting that the dust surrounding the object possesses unusual physical properties. When unpolarized sunlight encounters dust particles, the scattered light becomes partially polarized. The degree and direction of this polarization depend on factors such as particle size, shape, porosity, and refractive index. By measuring polarization at different phase angles, the angle formed by the Sun, the object, and the observer researchers can infer details about the dust's physical characteristics. For most comets, the polarization curve follows a typical pattern. At low phase angles, comets exhibit a negative polarization branch, where the electric vector of the reflected light aligns perpendicular to expectations. This negative branch usually ranges from 1% to 2%, with an inversion point occurring around 20 degree June, 25 degree rounds, beyond which the polarization becomes positive. 3I Atlas does not fit this pattern. observations show a deeper negative polarization minimum, reaching about 2.7% at a phase angle near 7°. Additionally, the inversion angle appears earlier, around 17°, rather than the usual 20° or higher. In combined datasets, 3I Atlas sits far outside the typical cluster of polarization values for both comets and asteroids. This deviation is not subtle. It occupies a region of parameter space that, until now, has been empty. These results imply that the dust grains in the coma differ from those commonly observed in solar system comets. Large grains, aggregates of smaller particles, or dust with unusual refractive properties could all generate deeper negative polarization. A composition rich in ices and complex organic compounds materials processed over long periods in interstellar space could also contribute to this behavior. The unusual polarization signature supports the idea that 3I Atlas may share properties with outer solar system bodies such as Kuiper Belt objects. Objects in that region are known to have surfaces coated with radiation-processed organic material, giving them a distinctive reddish coloration and low albedo. If 3I Atlas formed in a similar environment around another star system, its surface may have accumulated comparable materials. Another factor is particle size. Polarization measurements suggest that large dust grains on the order of 0.1 millimeters or greater are present in significant quantities. This aligns with earlier estimates indicating that the dust released by 3I Atlas may be dominated by large aggregates rather than fine particles. Large grains respond differently to radiation pressure and remain in the coma longer, contributing to the observed scattering properties. The potential role of plasma interactions must also be considered. Dust grains exposed to a dense plasma environment can accumulate electric charge. Charged grains respond to electromagnetic forces and may align with magnetic fields. Such alignment could influence polarization by imposing a directional preference on the scattering process. While this idea remains speculative, it connects polarization anomalies to the earlier plasma shield hypothesis. However, polarization data alone cannot conclusively determine particle shape, composition, or charge. Polarimetry works best when combined with spectroscopic and imaging data to cross-check interpretations. One challenge is that polarization curves are sensitive to many parameters at once, and multiple combinations of grain size, porosity, and refractive index can produce similar results. The deep negative branch observed in 3I Atlas restricts the range of possibilities but does not isolate a single solution. Another complication involves model dependence. Researchers use computational scattering models to interpret polarization data. These models rely on assumptions about dust morphology and composition. If the actual dust environment of an interstellar object differs significantly from these assumptions, the models may misrepresent physical conditions. In this case, the unusual polarization of 3I Atlas could reflect limitations of existing models rather than truly exotic dust properties. Despite these challenges, several conclusions can be drawn with confidence. The dust environment of 3I Atlas differs substantially from typical solar system comets. the observed polarization minimum and early inversion angle fall outside normal ranges. Large grains likely dominate the coma. This conclusion aligns with both polarization data and independent mass production estimates. The dust composition may include significant organic material. This is consistent with an object formed in a cold outer region of another star system. Plasma interactions may modify the scattering properties of dust. Charged grains in a magnetized environment could influence observed polarization. These conclusions reinforce the broader pattern emerging from the study of 3I Atlas. Every major observation visibility, acceleration, composition, and polarization reveals an object that differs from typical comets in multiple respects. None of these differences individually suggest anything beyond natural variation, but together they paint the picture of a body shaped by long-term exposure to interstellar conditions. Polarimetry also offers indirect insight into the surface properties of the nucleus. Although the nucleus itself has not been imaged, the composition of the dust in the coma provides clues about the materials being shed. If large aggregates of icy and organic matter dominate the dust cloud, the nucleus likely possesses a thick radiation-processed crust. Such a crust could develop over millions of years as cosmic rays alter the chemical structure of surface ices. This process can convert simple molecules into more complex organics, darkening the surface and influencing sublimation behavior. This type of radiation processing may explain several observed anomalies. A surface enriched in complex organics could suppress water sublimation while allowing more volatile compounds such as carbon dioxide to escape. This would align with the unusually high CO2 to water ratio observed in spectral data. It could also influence how dust is released, favoring larger particle clusters over fine grains. The deep negative polarization branch observed in 3I Atlas is consistent with such a radiation-processed surface. Similar polarization behavior has been detected in outer solar system bodies exposed to long-term cosmic ray bombardment. Interstellar processing could amplify these effects, producing even more pronounced signatures. Polarization data will continue to play a central role in understanding the object. Additional observations at different phase angles, wavelengths, and distances from the Sun will refine the polarization curve. Researchers will also compare the data to laboratory simulations and computational models to improve interpretations. Despite challenges, polarimetry remains one of the most sensitive tools available for studying the physical properties of dust environments around distant objects. Ultimately, the polarization signature of 3I Atlas reinforces the conclusion that the object is unusual but not inexplicable. Its dust environment, shaped by interstellar chemistry and cosmic ray processing, contributes to the unique observational profile. While the data do not reveal a single definitive cause for the visibility paradox, they strengthen the argument that multiple factors — composition, grain size, plasma interactions — combine to produce the object's distinct appearance. The chemical composition of 3I Atlas is one of the areas where the object diverges most sharply from typical comets. Early infrared observations using the James Webb Space Telescope revealed a carbon dioxide to water ratio of roughly 8.1. For every molecule of water released into the coma, 8 molecules of carbon dioxide were detected. This ratio places 3I Atlas far outside the distribution of known solar system comets, which usually exhibit CO2 Ca H2O ratios ranging from 0.03 to 2. Even the most CO2-rich comets rarely reach a ratio of 1.1. The value observed for 3I Atlas falls about 6 standard deviations beyond the highest solar system measurements. Such a high abundance of carbon dioxide relative to water suggests that the object formed in an environment significantly colder than the region where most solar system comets originated. In our system, water ice dominates beyond the snowline, typically around 2 to 3 astronomical units from the Sun, while carbon dioxide condenses efficiently only much farther out, where temperatures are extremely low. If 3I Atlas formed in a similarly cold region of its parent planetary system, this could explain the unusually high CO2 abundance. Another possibility involves long-term cosmic ray processing. An object traveling through interstellar space for millions or billions of years is continuously bombarded by high-energy particles. These particles can penetrate the surface layers of ice and alter their chemical structure. One well-studied outcome is the conversion of carbon monoxide into carbon dioxide. If the object originally contained significant carbon monoxide ice, cosmic ray exposure could gradually transform much of it into carbon dioxide. Cosmic ray irradiation also produces complex organic materials, commonly referred to as tholins. These substances accumulate over time, forming a dark reddish crust on the surface of icy bodies. This crust affects the thermal properties of the nucleus by insulating deeper layers and altering sublimation rates. When such an object enters a solar system and begins to heat up, the outer organics may limit the release of water vapor while allowing more volatile compounds like carbon dioxide to escape more readily. This model explains several observed features simultaneously: the extreme CO2 to water ratio, the presence of large dust grains consistent with cohesive organic crust fragmentation, the unusual polarization signature of the coma, the steep activity profile as the object approaches the Sun. Together, these characteristics match expectations for a body that has experienced prolonged exposure to interstellar radiation. Spectroscopic observations further support this picture. Besides water and carbon dioxide, 3I Atlas shows faint signatures consistent with other volatile species, including possible traces of carbon monoxide, methane, and nitrogen-bearing organics. These detections remain tentative and require additional observations, but they align with a formation environment rich in volatile ices. The dominance of carbon dioxide has implications for the thermal evolution of the object. CO2 sublimates at lower temperatures than water, meaning the object becomes active at greater distances from the Sun. This early onset of activity matches the observed long-range mass loss and associated non-gravitational acceleration. It also suggests that the thermal wave does not reach deeper layers where water ice remains insulated by the organic crust. Large grain dust production represents another anomaly. Comets in our solar system typically release a mixture of fine and coarse particles. However, analyses of the coma of three-eyed Atlas indicate a predominance of grains approximately 0.1 mm in size or larger. Such grains require stronger outgassing pressures to escape the surface, implying either unusually strong sublimation or surface layers with cohesive strength that release dust in clumps rather than fine particles. This behavior aligns with laboratory studies showing that organic rich crusts formed through cosmic ray processing can bind smaller grains together into aggregates. When these aggregates detach, they behave like larger particles. Their size reduces the influence of radiation pressure, making them less responsive to solar forces and more persistent in the coma. The presence of large grains also contributes to the observed visibility discrepancies. Coarse dust scatters light more uniformly across wavelengths, reducing the contrast of fine features. This broad scattering effect could add to the photon diffusion caused by a plasma-rich environment, collectively producing the uniform brightness patches seen in high-resolution orbital imagery. From a statistical standpoint, the composition of Three-Eye Atlas raises important questions about the diversity of interstellar objects. Prior to this observation, only one interstellar comet 2I Borisov had been analysed spectroscopically. Borisov exhibited elevated levels of carbon monoxide, but otherwise resembled long-period comets from our own Oort cloud. Three-Eye Atlas, by contrast, appears to represent a more extreme chemical environment. If future observations identify additional objects with similar compositions, this would suggest that many planetary systems form volatile-rich bodies in distant cold regions, with cosmic ray processing playing a major role in shaping their surface chemistry. A critical challenge in interpreting the composition data comes from model dependence. Infrared spectroscopy provides detailed molecular signatures, but converting these signatures into abundance ratios requires assumptions about temperature, viewing geometry, and emission efficiency. While the CO2 on H2O ratio appears robust, uncertainties remain regarding the absolute quantities of minor volatiles. Continued observations across a wider wavelength range will help refine these estimates. Another question concerns the internal structure of the nucleus. If the surface is coated with a thick organic crust, sublimation may occur primarily through fractures or weaker regions in the crust. This would influence jet distribution and activity patterns, complicating models of mass loss. In such a case, even strong CO2-driven jets might remain difficult to observe if obscured by dust or plasma. The possibility of an artificial origin occasionally arises in discussions of unusual interstellar objects. In the context of Three-Eye Atlas, this speculation focuses on whether the high CO2 abundance could represent engineered camouflage. While such ideas draw attention, there is no evidence supporting artificial processes. The chemical and physical signatures match natural outcomes of long-term cosmic ray exposure and cold environment formation. As with previous anomalies, natural explanations remain entirely sufficient. Overall, the chemical composition of Three-Eye Atlas strengthens the conclusion that it is fundamentally different from typical solar system comets, shaped by a distinct origin and extensive interstellar processing. The extreme carbon dioxide abundance, organic-rich dust, and large particle coma contribute to several of the object's unusual observational properties. As the investigation continues, composition data will play a central role in evaluating the remaining hypotheses. These include understanding polarimetric behavior, assessing plasma interactions, and modeling the thermal and dynamical evolution of the object. Integrating spectroscopic results with polarization and acceleration analyses will help clarify how these diverse anomalies fit together into a cohesive physical model. As the investigation into 3I Atlas expands, it inevitably encounters more speculative interpretations. These ideas gain attention partly because interstellar objects are rare, and partly because several features of 3I Atlas do not fall neatly within established categories. While the scientific consensus remains firmly grounded in natural explanations, a careful assessment of alternative theories is essential for a complete analysis. The most discussed speculative hypothesis concerns the possibility of an artificial origin. This concept entered mainstream debate after the arrival of 1I Oumuamua, whose unusual shape and non-gravitational acceleration prompted some researchers, notably Avi Loeb, to propose that it might be a technological object, such as a thin solar sail. Although subsequent studies have identified plausible natural mechanisms for Oumuamua's acceleration, the discussion left a lasting impact on how interstellar anomalies are perceived. For 3I Atlas, artificial origin proposals emerge mainly because the object displays multiple unusual characteristics. Its extreme carbon dioxide to water ratio, its deep negative polarization branch, its large dust grain dominance, its visibility inconsistencies, and its modest but non-trivial non-gravitational acceleration. Individually, each feature can be explained by natural processes. Combined, they form a profile that challenges straightforward classification, making the object an attractive candidate for speculative interpretation. Proponents of artificial origin ideas argue that if a technologically advanced civilization wanted to disguise a probe or interstellar device as a natural object, coating it in ice and organic material would be an effective strategy. Over time, this coating would evolve chemically under cosmic ray exposure, producing the same radiation-processed surface seen on 3I Atlas. A plasma environment, if controllable, could obscure fine details from high-resolution observation while allowing the object to remain detectable at longer wavelengths. This line of reasoning suggests that the visibility paradox could represent intentional design rather than environmental effect. However, the scientific shortcomings of such interpretations are significant. Artificial origin hypotheses rarely offer falsifiable predictions, making them difficult to test. They can accommodate any observational anomaly by proposing an unknown technological mechanism. In contrast, natural explanations rely on measurable physics, such as sublimation, plasma interactions, and radiative processing. Additionally, the observed features of 3I Atlas do not violate any known physical laws. Although unusual, its properties align with expectations for a comet heavily processed by cosmic rays, formed in a cold region of a distant planetary system and interacting with the Sun's environment under atypical conditions. Nothing in the available data requires invoking artificial processes. A more conservative, but still alternative framework involves extreme natural variation. The diversity of planetary systems in the galaxy indicates that comets formed around other stars may differ significantly from those in our own system. Infrared surveys of protoplanetary disks show wide variation in ice composition, grain size, and chemical mixtures. Many disks contain regions colder than any in our solar system, where carbon dioxide and carbon monoxide dominate over water. In such environments, bodies like 3I Atlas could form as a natural class. The plasma shield hypothesis also fits within this natural framework. If the object outgasses large quantities of CO2 and CO, the resulting ionization under solar UV radiation could create a dense plasma envelope. This would affect the appearance of the coma and could explain why high-resolution instruments detect less structure than long-exposure amateur systems. Some researchers consider whether the object could possess a small intrinsic magnetic field. While comets are not normally magnetized, certain interactions between dust, plasma, and electric currents can induce transient magnetic structures. These structures could alter the distribution of plasma near the nucleus, potentially influencing both visibility and acceleration. Such a mechanism remains speculative, but falls within the scope of natural plasma physics. Artificial origin speculation also frequently references the idea of cloaking or active obscuration. In theoretical terms, plasma-based cloaking technologies are physically plausible. Magnetically confined plasma can scatter or absorb electromagnetic radiation across specific wavelengths. However, achieving the stability required for sustained cloaking would require precise control mechanisms far beyond anything observed in the behavior of 3I Atlas. Moreover, the object exhibits no regular energy output, thermal anomalies, or directed emissions that would indicate technological activity. Infrared observations provide an additional constraint. If the object were powered internally or used energy for propulsion or cloaking, its thermal signature would likely show elevated temperatures inconsistent with passive heating by the sun. So far, infrared measurements reveal no such anomalies. The observed emissions match expectations for sublimating volatiles and warm dust, not internal power generation. Radio observations also show no evidence of artificial signals. The detected radio emissions correspond to natural hydroxyl transitions produced when water molecules break apart under solar UV radiation. Detailed analysis of line ratios and frequencies shows no deviations that would suggest modulation or embedded carrier signals. Another important consideration is that extraordinary claims require extraordinary evidence. Natural explanations for interstellar objects have so far proven sufficient for all observed cases. While anomalies exist, such anomalies tend to diminish as more data becomes available. The history of astronomy includes many examples of unusual observations later explained through improved modeling, higher quality data, or a better understanding of environmental interactions. Nevertheless, investigating these alternative theories provides value. It encourages a thorough review of all observational evidence, highlights model uncertainties, and helps ensure that assumptions do not prematurely limit interpretation. A responsible scientific approach involves considering all hypotheses, evaluating them against available data, and favoring those supported by measurable, reproducible evidence. In the case of 3I Atlas, the natural explanation remains the most consistent with observations. The object's composition fits models of cosmic ray processing and cold environment formation. The polarization behavior aligns with large radiation-processed grains and organic-rich dust. The visibility paradox can be explained by plasma scattering and observational geometry. The acceleration aligns with CO2-driven outgassing from an interstellar nucleus. No direct evidence supports technological activity. As additional data from upcoming observations becomes available, including multi-wavelength monitoring during the solar storm, the analysis will become more precise. If new anomalies appear that cannot be explained by natural mechanisms, hypotheses will adjust accordingly. Until then, artificial origin theories remain speculative and unsupported by measurements. The relationship between scientific inquiry and public interpretation is also important. In a media environment where unusual astronomical phenomena often attract dramatic explanations, clarity and careful communication are essential. Maintaining a distinction between speculation and evidence-based analysis ensures that the investigation stays grounded in physical principles while remaining open to new data. Ultimately, the significance of 3I Atlas does not depend on whether it is natural or artificial. Its unusual properties provide an opportunity to refine models of interstellar object behavior, improve observational techniques, and expand understanding of how diverse the outputs of planetary systems can be. The anomalous features challenge assumptions and drive scientific progress, regardless of their origin. Understanding why 3I Atlas appears differently to various observers requires a closer examination of geometry, viewing angle, optical depth, and radiative transfer effects. These factors influence how much structure in the coma and nucleus becomes visible, and they can amplify or suppress features depending on the observer's position relative to the sun, the object, and the surrounding material. A key concept is the phase angle, which defines the separation between the sun, the object, and the observer. Comets often show dramatic differences in appearance depending on this angle. At small phase angles, known as forward scattering, geometry sunlight passes through dust before reaching the observer. Large dust grains in particular can strongly forward scatter light, creating an enhanced brightness that may mask fine structural detail. Conversely, at large phase angles, backward scattered light becomes dominant, reducing the forward scattering enhancement and improving contrast in the coma. During the early observations of 3I Atlas, Many of NASA's orbital images were taken under low to moderate phase angles, where forward scattering can obscure jets or density gradients within the coma. This could explain why amateur astronomers, observing from different parts of Earth under varying angles and conditions, reported features that HiRISE did not. Small differences in viewing geometry can produce disproportionately large differences in apparent coma structure. Another major consideration is optical depth. Optical depth describes how transparent or opaque a medium is to light. A highly optically thin coma allows observers to see internal structures, jets, or the innermost regions near the nucleus. A higher optical depth, caused by dense dust or plasma scatters, and absorbs more light, creating a uniform brightness distribution that obscures detail. Even if the nucleus emits strong localized jets, they may be hidden by multiple scattering events within the surrounding dust. This effect becomes especially pronounced if the coma is rich in large grains. Large particles scatter light across a broader range of angles and wavelengths, acting as a distributed diffuser. This produces the smooth, featureless glow observed in some datasets. If the coma contains an additional scattering component, such as ionized gas or plasma, the combination can dramatically reduce contrast. The contrasting datasets between amateur and professional observations can therefore be explained by variations in optical depth, viewing geometry, wavelength sensitivity, and exposure strategy. Amateur observers often use long exposures and stack multiple frames to enhance faint structures. This method effectively increases the dynamic range and reveals low contrast features. Spacecraft instruments, optimized for fast imaging and specific spectral ranges, may saturate or under-respond to extended low-surface brightness regions. When combined with scattering effects, this can cause structural details to vanish entirely from high-resolution images. Radiative transfer modeling provides a framework for analyzing these issues. Radiative transfer describes how light propagates through a medium that absorbs, scatters, and re-emits radiation. In a dense, irregularly structured coma, radiative transfer effects can create complex patterns in brightness that depend on particle size, density gradients, and wavelength. Even without exotic plasma behavior, these processes can produce the kind of visibility paradox observed in 3I Atlas. A related phenomenon involves shadowing and anisotropic scattering. If the nucleus has an uneven surface or the jets emerge from narrow vents, parts of the coma may be illuminated unevenly. At certain angles, these asymmetries appear as jets or arcs. At other angles, they vanish. This can lead to apparent contradictions across datasets taken at different times or from different positions. These effects also help explain the ring-like structures reported by several amateur astronomers. Ring patterns can arise from density waves in the coma, spiraling jet emissions due to nucleus rotation, or projection effects when a conical jet is viewed nearly end-on. Without precise rotational and thermal data, these interpretations remain uncertain. However, such structures do not require artificial or exotic explanations. They naturally result from radiative and geometric effects in cometary comae. Another aspect influencing visibility is wavelength dependence. Different wavelengths penetrate dust and plasma to varying depths. Infrared light, for example, can pass through dusty regions that obscure visible wavelengths, while ultraviolet observations may highlight ionized gas rather than dust. Instruments observing at different wavelengths will therefore present different structural signatures. A feature that is invisible in visible light may appear clearly in infrared or ultraviolet. A practical example is the detection of the hydrogen envelope by the MAVEN spacecraft. While high-rise images appeared featureless, ultraviolet data revealed extended hydrogen emissions produced by water photo dissociation. This shows that the object emits complex multi-wavelength signatures even if visible images do not show structure. The interaction between CO2-driven sublimation and radiative transfer effects adds further complexity. Carbon dioxide is more volatile than water and produces fast-moving gas flows that can drive larger dust grains into the coma. These grains, once ejected, can remain suspended for extended periods. Their presence increases the optical depth and reduces the visibility of internal structures. Combined with possible plasma scattering, these effects can create a coma with smooth brightness profiles, even if strong jets are present underneath. Understanding these interactions requires time-dependent modeling. The coma is not static. It evolves as the object rotates, changes distance from the sun, and interacts with solar wind variations. A comprehensive radiative transfer model must incorporate dynamic dust release, grain fragmentation, plasma density changes, and anisotropic outgassing. Such models reveal that small variations in initial conditions can produce large differences in observable features, which explains the variability seen in amateur images. The interplay between viewing geometry, optical depth, dust properties, and plasma effects is sufficient to explain all current visibility discrepancies without invoking exotic mechanisms. The radiative transfer framework also helps set expectations for upcoming observations. If the solar storm alters the plasma density or dust distribution, the optical depth may change rapidly, causing jets, arcs, or structural gradients to either emerge or disappear depending on the wavelength. In practical terms, the best way to resolve the visibility paradox is through coordinated, multi-wavelength observations during periods of dynamic environmental change, such as the predicted CME event. If structural features become visible in infrared or ultraviolet wavelengths, but remain hidden in visible light, radiative transfer effects will be the most likely explanation. If features appear suddenly in all wavelengths following a disturbance, plasma scattering may be the dominant factor. If visibility remains unchanged, the coma may simply be too dense or too uniform for any instrument to resolve structural detail. In summary, radiative transfer and geometric effects offer a natural, well-understood explanation for why 3I Atlas appears differently across instruments. These processes depend on particle size distributions, dust density, viewing angles, and wavelength sensitivities, rather than requiring any unusual or artificial mechanism. Understanding these interactions will be essential for interpreting the next phases of observation and for integrating the visibility data with compositional, polarimetric, and dynamical analyses. A complete physical interpretation of 3I atlas also requires understanding how the object rotates and how rotation influences its activity. Rotation affects jet geometry, dust distribution, thermal gradients, and non-gravitational acceleration. For most comets, measuring rotation is straightforward. Variations in brightness across time reveal periodic fluctuations caused by surface features and changing jet orientation. However, the rotation state of 3I atlas remains uncertain due to conflicting observational signals and the limitations imposed by the visibility paradox. Initial photometric attempts to measure rotational periodicity have yielded inconsistent results. Some observers reported brightness variations on timescales of 7 to 9 hours, while others suggested much longer periods, potentially exceeding 20 hours. The lack of a consistent, repeatable light curve makes it challenging to determine whether the nucleus rotates rapidly, slowly, or irregularly. Variability in coma properties may overshadow nucleus-driven changes, making photometry unreliable. This ambiguity raises the possibility that the rotation state of 3I atlas could be non-principal axis rotation, often called tumbling. Tumbling occurs when an object rotates simultaneously around multiple axes rather than a single stable axis. Several solar system comets, including 2P Carl-Encke and 103P Hartley, have exhibited such motion. Tumbling can arise naturally from uneven outgassing forces or past collisional events. For an interstellar object that has travelled for millions of years through varying gravitational fields and radiation environments, the likelihood of a disturbed rotation state is significant. If 3I atlas is tumbling, the orientation of jets would change unpredictably over short timescales. This can produce inconsistent brightness fluctuations and unstable jet signatures. Under certain circumstances, a tumbling nucleus can also cause dust structures that appear as spirals or arcs when viewed from specific angles. Some amateur reports describing spiral-like or ring-like features in the coma could align with this interpretation, though geometric and radiative effects may also contribute. Another factor is jet collimation. Comets often produce jets from localized vents where subsurface volatiles escape through fractures. The direction and intensity of each jet depend on surface illumination and thermal conditions. If jets originate from small regions on a rotating nucleus, the overall appearance of the coma will vary periodically as the jets sweep through space. In the case of 3I atlas, the absence of clear jet structures in high-resolution imagery prevents direct identification of vent locations. The energy balance of the nucleus also plays a central role. The sublimation rate depends on solar irradiance, thermal conductivity of the surface materials, and the insulating effect of radiation-processed crusts. If the surface is coated with an organic-rich layer formed through cosmic ray processing, as suggested earlier, the thermal wave may penetrate unevenly. This could restrict sublimation to weaker or fractured regions, producing irregular jet patterns. Models of internal layering can help interpret these effects. Interstellar objects are expected to develop stratified layers as cosmic ray processing selectively modifies the uppermost surface. Beneath this layer, water ice, carbon monoxide, and other volatiles remain relatively pristine. When heating begins, outer layers suppress water sublimation, but allow deeper, more volatile ices to escape through fractures. This is consistent with the high CO2 production observed in 3I Atlas and may influence jet structure. Another important variable is torque. Outgassing produces rotational torque when jets are directional rather than symmetric. For many comets, this leads to measurable changes in rotation rate over time. In extreme cases, outgassing torques can accelerate or decelerate rotation significantly within a single perihelion passage. If 3I Atlas experiences strong asymmetric outgassing, this could explain why rotational periodicity has not stabilized into a clear pattern. If the rotation rate is changing rapidly, attempts to measure periodicity would produce inconsistent results depending on the observational epoch. Accelerating spin can also push an object into or out of tumbling states. Numerical models show that small nuclei less than a few kilometers in diameter can transition between stable and unstable rotational modes when subjected to sustained asymmetric forces. The thermal model further influences how jets behave. A steep thermal gradient across the surface can cause one hemisphere to dominate activity, depending on rotational axis orientation. If 3I Atlas has a high obliquity, one region may experience prolonged solar illumination, increasing sublimation rates, while the opposite region remains cold and inert. This creates asymmetrical activity that can contribute to both non-gravitational acceleration and complex coma structures.